So Ashi's going to talk. Ashi's talk is called Mind Over Matter with Math, Exploring the Banach-Tarski Theorem. Did I pronounce that correctly?
Banach.
Banach.
There's an extra R in there.
Oh, there was an extra R. Oh, so the Banach.
I think I misspelled it.
Ah, all right. So, Ashi is a freshman originally from Ellicott City, Maryland. Go Maryland.
Woo! She's
an avid fan of math and computer science who hopes to work in social good one day. Ashi.
Hi everyone, thanks Jeff for the intro. So when I say math, what do you guys think of? Just like with a show of hands, you can tell me what you think of math.
Failure.
Any other words from the mind?
Numbers.
Okay, fair. So I'm not hearing a lot of positive things, which actually is pretty common. And a lot of people are like, okay, Ashi, like seriously, like why do you like math? And that's common here, even here at Stanford. Here at Stanford, we're hailed as like, you know, yes, we're liberal at school, but we're more techie. Like people must really like math here. But even here, like a lot of people think to have fun in your discipline or to actually like your discipline, you need to combine that with some type of humanities. And yes, the humanities are great, but so is math. Math is really, really pretty. And don't believe me? You will after this talk. So a lot of times when you are in class and you say, okay, prof, like, what are we doing? Why are we doing this math thing? They're like, well, it has these applications in engineering or et cetera, et cetera. And sure, math is cool for that reason. But I also think math is cool just by itself. So first I'm going to talk a little bit about sets because I want to talk about infinity. Now infinity is really, really weird. Like honestly, that's the best way to describe it. Infinity is crazy. There's also this concept where there are different levels of infinity. So you think, okay, infinity just means that they're just like infinite things. Like it's more than the however many I can count. So there's just one infinity. So actually that's not true. They're like different levels of infinity, which is crazy. Like, what? So on that level, math is cool because like, what? So first of all, I'm going to talk about sets. So I'm going to define how we can tell if two sets are the same size. So let's take this pile of 3 books and this pile of 3 books. I can tell you that these piles are the same size for this reason. I can take every book in this pile and map it to a different book in this pile, and I can take every book in this pile and map it to every book in this pile. Let me show you what I mean. This book gets mapped to this book. This book gets mapped to this book. And then this book gets mapped to this book. So I can tell you that they're all the same size. And I don't have any books left over, right? Everyone makes sense? Good. Cool. So now I'm going to extend this to actual numbers. So let's take the two sets 0 to 1, including all real numbers in that set, including 0 and 1. And then let's take the set 0 to 2, including all real numbers in that set, and 0 to 2. And you're going to tell me, Ashi, all right, there's no way that these sets are equal. Like, 0 to 2 is obviously bigger than 0 to 1, right? Like, no way that they're equal. But let's think about this for a moment. Any number in my second set, 0 to 2, is twice of any number from 0 to 1. So I compare a number from 0 to 1, multiply it by 2, and get a number from 0 to 2. And you're like, okay, but there's still numbers in 0 to 2 that aren't in 0 to 1. But let's think about this a little bit more, right? So for any number in 0 to 2, I divide it by 2, and it's in 0 to 1. And notice I didn't say natural numbers. So, I mean, those sets are equal to, but if we're talking about infinities, like these two infinities are the exact same size. So this set, 0 to 1, is the exact same size as 0 to 2. Now, if we're looking at natural numbers, 0 to 1, 0 and 1, that's 2 numbers, right? 0, 1, 2 is 3 numbers, so those aren't the same. But once we introduce infinity, like, this gets weird. Like, suddenly these are the same size. So this is just to get a sense of like how weird infinity is. I don't expect this to make sense exactly right now. That's fine. You have to think about it for a little bit and then be like, yeah, I guess that's weird, but it could make sense in a way. So we're going to shift gears a little bit. I want you to imagine a sphere. Now, this is going to be an actual sphere until I actually get into the theorem, but it's going to be a sphere that we can imagine in real life. Now, in real life, if we take a sphere, it's made of a finite number of atoms. Because matter, it's finite. You have atoms, right? So there's a way to divide this sphere into two equally sized spheres, as long as the density of those two spheres is half of what it was earlier. Make sense to everyone? Cool. Okay, so now let's introduce infinity into this. Consider instead a mathematical sphere. That means basically, instead of it being a physical sphere, they're actual atoms, they're an infinite number of atoms. It's just atoms, well, not atoms, but points. There are points everywhere. Now, what the Banach-Tarski theorem says is that you can take that original sphere and make it into two spheres of the same size that are the same density. Basically, you get two spheres that are the exact same density as your first sphere. And it's not like you're adding points to it or taking away points. You're taking the same number of points from the original sphere and making it into two spheres of the same size, of the same density. What? Like, that's crazy. This is why I like math, because it screws with my mind, and I sit there and I think, okay, like, at first I thought that makes sense, but then I thought about it, and it didn't make sense. And theoretically it makes sense, but that's crazy, guys. Like, you can take something of one size and turn it into two things of the same exact size. That's why I like that.